Let's proceed from where we ended in the previous video now to measure the fluids of the fluid compartments. So we've talked about the body having ECF and ICF, ECF being divided into plasma, interstitial, and transcellular. Now, how do we get to measure those fluid compartments? So we are going to use what we call the dilution method. Now, what the aim of this method is that when the liquid you are using to mark where water is in the body, it should be able to go at every point where the liquid you want to measure is. So if I want to measure the total body water, I need to make sure that at every point in the body where there is water, this fluid which I'm using or the dye which I'm using should go at every point where there is water. So there are some six properties of the dye that we need to choose. The first thing is that it must mix evenly throughout the compartment. If I want to measure the total body water, it should go from the head to the toes, and then it should not be toxic, meaning it shouldn't affect any physiological activity. If my body operates in this way, if that thing is injected, that dye is injected, it should not affect the operation of the body. And then it should be even mixing, so it should mix even, it shouldn't be concentrated on one point and not on the other. So basically this is the same as but the first one. It must not have, if it have, it must have no effect of its own on the distribution of water and other substances. So if this liquid or this dye has been injected in the body, it should not affect the way liquid is distributed. So water now starts concentrating on one side, or it is affected like that. That is affecting, of course, physiological activity, and it must not be unchanged during the experiment of its own. Or if it is unchanged, the amount that is changed must be known. So meaning if we inject 2 grams of this dye, it should remain 2 grams. Or if it changes and then at the end we have got 1 gram, we should know the amount that has been removed. And then the material should be relatively easy to measure. That is another property. So the method that we use is called the Stewart-Hamilton dye dilution method. If I want to measure total body water, I can use D2O. If I want to measure the ECA fluid which is found just outside the cell, I can use mannitol and sucrose. That is because mannitol and sucrose, these will not be able to penetrate to go into the cells, right? It can only remain outside the cells. And then specifically if I want to measure plasma, I can use Evans blue because it can't go outside the blood vessels. So those methods, so these three we have talked about, these are called direct methods because you are using a dye directly. Now, as we can see, we don't have a direct method of measuring interstitium, meaning we are going to use an indirect method. So for the interstitium and the ICF, we use indirect methods. For ICF, if I know total body water and then I've measured ECF, we know ICF plus ECF is total body water. So I'll simply remove ECF from total body water to find ICF. Interstitium, we know that if we add interstitium and plasma, we are going to get ECF. So if I know ECF and plasma, I'll simply subtract plasma from ECF and then I'll get the interstitial. And then the direct methods, we have got blood volume, plasma volume, ECF, and also the others like that. So for volume, how do you now measure the volume that has been calculated if I get to add this dye into the body? So we are going to say amount which is injected minus amount that is excreted divided by concentration of the same dye which we had put in the body. Sometimes you'll not have anything that is excreted, and so in that case, we're just going to say amount injected divided by concentration. We already said in the previous video that plasma volume is given by blood volume is given by plasma volume over 1 minus hematocrit. Hematocrit is just the number of red blood cells in the body. We can have other dyes we are able to use. For plasma, we want a dye that can't cross the capillaries, which will just remain in the blood vessels. So we can use iodinated albumin, we can use Evans blue. For ECF, we want something that cannot go into the cells. So we can use the thiosulfate, we can use iothalamate, we can use sodium, we can use inulin. And inulin is the best that we're able to use. Of course, we are using also. Now, sometimes we'll not be able to see some of these, but they've just given this sodium, the iothalamate, and thiosulfate. We should be able also to know them. Of course, we have got also sucrose, mannitol. In testation, we have said we don't have a direct method. You just say ECF minus plasma. Total body water, you can use antipyrine, you can use heavy water, which is D2, or you can use also triated water, or those. And then for ICF, we said you can't measure direct. You just say total body water minus ECF. Now for blood volume, we want something that will mark together not only plasma but also the cells. So you can use chromium labeled red blood cells, or you can use the direct formula to say blood volume is plasma volume divided by 1 minus hematocrit. We also have what is called lean body mass. Lean body mass is the fat-free mass. What do we mean? We're talking about that mass that does not have any fat. That is what we refer to as lean body mass. So for total body mass is going to be given by the fat mass plus fat-free mass. Fat mass plus fat-free mass. So we also need to take note of that fat is relatively anhydrous, meaning that it does not mix with water. So because of that, the water content of lean body mass is going to be constant. What are we saying? The water content of the lean body mass. Lean body mass is the mass that does not contain any fat. So it's going to be constant. In this case, we are going to say that water that is found in that portion in the lean body mass, the mass that does not contain any fat, for every 100 grams of a tissue, we are going to have 70 mils of water, because in this tissue we are not going to have any fat. We will not have any fat there. All right, let's consider an example. For a health adult male weighing 70 kg, what is the lean body mass? What is his fatty mass? How do we work out this question? So to be able to calculate this one, let's first calculate the total body water. Now I've been told that this is a 70 kg old man. Total body water, we know that is 60% of the weight. So times the weight, which is 70 kg. 60%, you know that is 60 out of 100. So this is going to give us 42 kg. Okay, now we know that for water, 1 liter is equal to 1 kg. So this will basically give us 42 liters. This is the total body water. Now already we have said that lean body mass is the that mass that contains no fat. Now for that mass which contains no fat, if we have got 100 grams of that, 100 grams of a tissue, then from that tissue we're going to have 70 mils being water. That is what we've said. It's the same as saying 70 mils per 100 grams or 100 grams per 70 mils. So if I've got now 100 grams of tissue, I'm going to have 70 mils of water. What if I've got 42 liters? How much mass do I expect? So I'm going to multiply. I've got a mils down, and then I'm going to multiply by the 42 liters. But we need to convert it to mils also. So multiply by 1000. So it will be 42,000 mils. So the mil will cancel with the mil here, and that is going to give us about 60,000 grams. Now I want to convert this to kg, so I'm going to simply divide it by 1000, and that is going to be 60 kg. So this is the mass that contains no fat. That is the lean body mass. So what is the lean body mass? Is 60 kg. What is its fat-free mass? We know that if we add the lean body mass plus fat mass, it should give us the total body mass. So the fat mass is going to be equal to the total body mass, or the total body weight, minus the lean body weight or lean body mass. So the weight of this person is 70 kg. Portion that has got no fat is 60 kg. Then the fat is just going to be 10 kg. So that is it for this one. Now, we need also to know that for the transcellular fluid, we said the transcellular fluid is the fluid which is found just in special cavities. For example, we have got the peritoneal fluid, pericardio. This is the fluid found in the heart. It's just about 50 mils. We say it's very small pleural cavity in the lungs, peritoneal fluid. So for males, there's no fluid in the peritoneal, and then for females, about 20 mils. That is in the luteal phase, and then 5 mils at the late luteal phase. And then for the synovial fluid, it is very small because the synovial joint is really small, like about 1 mil. So this is just showing us that these transcellular fluids are really, really very small. Even if you add all of it, this will not even give us a liter. So transcellular fluid is about 1 to 2 liters. That is 1% to 3% of the total body weight. Okay. Now let's consider this question. A 30-year-old pregnant woman in a 37-week of gestation is found to be carrying a macrocosmic baby who is 5 kg in weight. Before she became pregnant, this woman was weighing 90 kg and only gained weight due to the pregnancy. Her total body weight currently is 95 kg. We can, of course, even calculate. The baby is 5 kg and then she's 90, so that would be 95 kg. Name the different body fluid compartments, the size of each, and ways in which they can be measured. And then compute the amount of water found in the intravesicular space of this pregnant woman. Find the ECF and ICF of this baby. And then compute the tissue fluid in this pregnant woman. Explain the reason as to why transcellular fluid is less than 1%. So starting with the first one, the first question, name the different body fluid compartments and also the ways in which they can be measured and the size of each. So, of course, we have already said body fluid compartments can either be ICF or ECF. So, ICF is a fluid found within the cells of the body. It accounts for 40% of the total body weight. We already saw this in the previous video. So, if you have not watched the previous video, please go on and watch it. Just follow this playlist. And then the size of the ICF, we know it can be estimated indirectly by measuring the extracellular fluid subtracting from the total body water. I've already mentioned that. Okay, so I've mentioned what the ICF is, the size, and also how it can be measured. And then for the ECF, ECF is the fluid found outside the cell. It can be further divided into two compartments, of course. Now, not necessarily that can be divided only into two. We saw it can be divided into three, but it's just that transcellular is mostly taken to be part of the interstitial in even some other books. So it accounts for about 20% of the total body weight. So we have got what is called the intravesicular fluid, which is also, of course, the plasma fluid. Intravesicular just means inside the blood vessels. So the intravesicular or the plasma is a fluid that is found inside the blood vessels. It constitutes 5%. Again, we found this in the previous video, so you can watch that. The size of the intravesicular fluid can be measured directly by techniques such as intravenous dye dilution or indicator dilution. Of course, we also saw some of the dyes which were able to use to find the plasma volume, such as albumin, iodinated albumin, and Evans blue. And then the interstitial fluid, this is the fluid that's around the cells, of course, and fills the spaces between them. It consists about 15%. Again, we found this value in the previous video. The size of the interstitial fluid can be estimated by subtracting the intravesicular from the ECF. We have just from mentioning this. To say interstitial, you find it indirectly. And then the transcellular is the smallest fluid compartment, accounting less than 1% of total body weight. It includes fluids such as the cerebrospinal fluid, synovial fluid, pleural fluid, peritoneal fluid. The size of the transcellular fluid is difficult to measure. So it is really difficult to measure because actually you just take this to be part of the interstitial. You don't have a direct formula that you're able, either a formula or a direct method, unless by experts to get to measure that. But it's really very, very small. All right. The next one, compute the amount of water found in the intravesicular space. Now, for this question, it is intravesicular space, not just anything. This is a space. In other words, if we look at this one, here we're talking about intravesicular fluid, which is just the fluid found inside the blood vessels. Now, for this question, it is intravesicular space, meaning in the blood vessels. So, in the blood vessels, we have got plasma and also we have got blood cells. So, if the question was saying plasma, we know that plasma adds up to what? 5% of the weight. But blood, the fluid found inside the blood vessels is blood. It is 8% because we're also including the cells. So intravascular space is different from just the intravascular fluid. The intravascular fluid, you are just talking about the plasma itself, but just everything found in the intravascular space, you are also going to include the blood. So it is 8% of the weight. I thought that would be important to mention even before we answer this question. So then, how do you work out that one? We are going to say for B, intravascular volume, which is simply blood volume, is 8% of the body weight. And now this woman is pregnant. She's 90 kg. The baby is 5 kg. So we'll use the total weight now. So this is going to be 8 out of 100 multiplied by the weight of the baby and the mother added. So that will be times 95. And this will give us about 7.6 liters. Okay. So that is going to be the value. What was the next question? Find the ECF and ICF of this baby. Right. So the ECF and ICF, if we are talking about a child, so in a normal man, like an adult man, ICF is about 40% of the weight, and then ECF is about 20% of the weight. So you can see that ECF is smaller than ICF. If we add ICF and ECF, it should give us the total body water, which is 60%. Now, specifically, we want to find for the baby. So ICF of the baby then is going to be 40% of the weight. Now, of course, we know that the baby's weight was 5. So that will be 40 times 5. And that is going to give us about 2 liters. And then ECF is 20% of the weight. So that will be times, I've already said of the weight. So this is going to be 20% of the weight. That is 20 times 5. And that is going to be, this is 20%, which is 20 out of 100 times 5. And that is going to be about just 1 liter. Okay, so that is going to be it. So we can see that the ECF is smaller, of course, than the ICF. So that is true. And then the next question, compute the tissue fluid of this pregnant woman. What is tissue fluid? Tissue fluid is the fluid which is found between cells. So basically, if we are talking about tissue fluid, we're simply talking about interstitial fluid. And interstitial fluid, we already know that plasma fluid is 5% of the weight. If I add plasma and interstitial, I should get ECF. And we know ECF is 20% of the weight. So interstitial is 15% of the weight. So that is going to be 15% of the weight. And the weight of the mother is 795 because she's pregnant. Include also for the baby. And that will give us about 14.25 liters. Explain the reason as to why the transcellular fluid compartment is less than 1%. We already mentioned that. Okay, so the transcellular fluid is relatively small compared to other fluid compartments constituting less than 1% of the body weight. This is because transcellular fluid are confined to specific spaces within the body, such as cerebrospinal fluid, synovial fluid, or pleural fluid in the lungs. These spaces have limited capacity to the overall volume of the body. So here we end with this tutorial. Thank you so much for watching. Please remember to subscribe.